And we are pleased today to have Russ Taylor from the University of Cape Town here at Georgia Tech. And he'll be giving the inaugural Bold Ideas in Physics public lecture that celebrates the life of David Ritz Finkelstein. But before we get into the science, we want to spend several minutes discussing the accomplishments of David Finkelstein. And for this, Dean Gobart will speak to you.
Me? Can you hear me? Good, terrific. Thank you very much. Excuse me while I take my glasses off. I'll be able to see my notes. I won't know who anyone is out there, but excuse me. Well, thank you, John, and good evening. It really is wonderful to see everybody here. As John said, my name is Paul Goldbart. I'm fortunate to serve as the Betsy Middleton and John Clark Sutherland Chair and Dean of Georgia Tech's College of Sciences. In a moment, I'll introduce tonight's speaker, Professor Russ Taylor from the University of Cape Town in South Africa. Russ, thank you very much indeed for joining us. But before that, I'd like to spend a few minutes telling you about a remarkable person, David Ritz Finkelstein, who sadly passed away at home in Atlanta 1 year ago tomorrow, aged 86. It is David's life and work that we are celebrating and commemorating through this evening's lecture and via the exhibit that will be on display until February the 19th for all to learn from out in the atrium of the Clough Undergraduate Learning Commons, the building we are in this evening. As I tell you a little bit about David, let me acknowledge that I shall lean on good work done by Stanford professor Lenny Susskind, a former professor of David's at Yeshiva University, and my friend and Georgia Tech colleague Robinson professor Predrag Svetanovich. Lenny and Predrag are themselves deep and accomplished theoretical physicists who, like David, are unafraid to challenge orthodoxy, and who, like many, greatly admire David for the breakthroughs he delivered to human knowledge. It's also a pleasure for me to warmly acknowledge Ray and Jody Franco for their support of the Georgia Tech Finkelstein Bold Ideas Fund, Kirk Henderson of the Georgia Tech Library for designing and putting together the exhibit about David's life and work out in the atrium of this building, Predrag Svetanovich, Ed Greco, Deirdre Shoemaker, and Maureen Ruhi for their work on this celebration of David's life and work, and of course, our guest of honor this evening, David's dear wife, Shlomit Ritz Finkelstein. Thank you for being here with us this evening, Shlomit. Thank you. We sometimes talk of science as that exquisite intersection of creativity, beauty, and impact. David Finkelstein truly lived at that intersection. David was born in New York City in 1929. He graduated from City College of New York, training ground of pioneers in many fields, with honors both in physics and mathematics. In 1953, he received his PhD in physics from MIT, with a thesis supervised by noted quantum field theorist Felix Villars. He worked at Stevens Institute of Technology from 1953 to 1960, at Yeshiva University in New York, an amazingly fertile environment where bold thinking was celebrated until 1976, and then here at Georgia Tech until just last year. Throughout his distinguished career, David was a man of extraordinary intellectual depth and honesty. I count myself as fortunate to have known him, but not fortunate enough to have known him well. I would love to tell you about the full range of his work, but that would take this whole evening and many more. So instead, I shall just touch upon a few of the highest high points. I mentioned that some of David's work was done in collaboration with friends, peers, students. I hope you won't mind that for the sake of simplicity, I shan't be naming them this evening. Only a year or two out of graduate school, David discovered a remarkable connection between spin that strange quantum motion exhibited by many particles, and the gravitational field, a connection thoroughly topological in flavor. The discovery led him to the speculation that all physical motion might be topological in origin, an intellectual vein that he would mine for much of his career. This was truly prescient work, predating by a decade and more the strong influence that topology would come to have in physics. By now, physicists see topology as an indispensable tool, for example, to understand exotic states of matter, such as the fractional quantum Hall state, and some of today's most exciting states, the topological insulators. You may know that the most recent Nobel Prize in Physics was awarded for theoretical discoveries of topological phase transitions and topological phases of matter. Then, only 5 years out of graduate school, David introduced his unidirectional membrane, which we now know of as the event horizon surrounding any black hole. Well, what is a black hole? You'll hear more about such things later on this evening, but it's matter so dense that not even light can escape its gravitational pull. For our sun to be a black hole, it would have to be smaller than the Georgia Tech campus. For the Earth to be a black hole, it would have to be smaller than the size of about a penny. By a very creative choice of coordinates, David's work showed that our understanding of physics remained sound at this event horizon, despite what less sophisticated readings of the equations would suggest. Thus, he showed us precisely how light and matter could fall through the horizon into the black hole, but could not return from it. This work had great impact, helping to move black holes and their parent topic, general relativity, from theoretical curiosities right into the mainstream of physics and triggering an avalanche of research that will rumble through physics and astronomy for as long as they are studied. Although today it is considered David's key contribution, this was for him only a step in his overarching program to bring topology into quantum physics. His next step, also highly creative, was to show that certain interesting models of the quantum world predicted particles, he called them kinks, that are extended over a finite volume rather than being concentrated at a point, and carry new types of charge and spin, all of topological origin. Again, ahead of its time and full of impact, introducing new concepts and changing the way physicists think. Even while making such seminal contributions to theory, David pursued a parallel career as a plasma physicist. He is remembered as an exquisite experimentalist and was proud of the theory he developed for ball lightning. During the summer of 1965, at the height of the civil rights movement, David took his family to Mississippi after receiving a temporary National Science Foundation American Physical Society appointment as a visiting scientist with the physics department of Tougaloo College, a historically black school. His efforts as acting department head included expanding the physics program and helping found the Public Radio Organization, whose goal was to offer African American people in central Mississippi unbiased news and a community forum. The courage of the people he worked with in Mississippi influenced David profoundly. In 1979, David became chair of Georgia Tech's School of Physics with the goal of raising its caliber. But when he failed to submit a budget, he was deposed by senior faculty. He emerged from this episode a changed man, recognizing that his mismatch with administration had the virtue of enabling his dream. He started his second life in which he dedicated himself to formulating a universal physical theory consistent with both quantum theory and gravity. Sidney Coleman, one of the leading quantum field theorists of the 20th century, said this of David: "He was a brilliant scientist with a passion for long shots. This meant that 9 times out of 10, he devoted his talents to ideas that do not pay off. 1 time out of 10, they do pay off. When this happened, his work was found to be of a great significance, extraordinary penetration, and 10 years ahead of everyone else's, as was the case when topological conservation laws entered the mainstream of quantum field theory." In all he did, in all he put his mind to, David took intellectual risks, avoiding safe questions guaranteed to have ready answers, and instead taking on deep, challenging problems of real significance and potential. In this, I like to think of him as a role model for all of us. This is what we scientists are here for. This is what these jewels, the research universities, are here for. And in all of his work, there is a beauty of a type that can be hard for non-scientists to discern. But let me just say that it is a beauty not unlike the beauty we sense when we look at a marvelous building, say the Taj Mahal. Symmetrical, harmonious, economical, everything necessary, nothing superfluous. And so it is with David's physics. David was a man whose mind carried him to the summit so that we might all peer over the event horizon and glimpse exotic lands, the black holes of Einstein's vision, our cosmos, and the remarkable LIGO scientific collaboration that Georgia Tech is so thrilled to be a part of today. We sometimes talk of science as that exquisite intersection of creativity, beauty, and impact. David Finkelstein truly lived at that intersection. Thank you.
Thank you for those wonderful words, Paul. First, I actually forgot to introduce myself. As my name is Professor John Wise, and I work in the School of Physics. But here today, we're going to hear from Professor Russ Taylor, and he is the director of the Inter-University Institute for Data-Intensive Astronomy, and he is a professor and SKA, meaning Square Kilometre Array, research chair at the University of Cape Town and the University of Western Cape. He's been playing a lead role in the development of the Square Kilometre Array since its inception. I mean, this is truly an engineering and computational feat of humankind because it will peer deeper into the cosmos using radio waves to unravel the mysteries of the universe. So let me say a few words about Russ Taylor. He received his bachelor's in astronomy and physics from the University of Western Ontario, and he received his master's and PhD from the University of British Columbia. And then afterwards, he held research positions at the University of Toronto, the Captain Astronomical Institute in the Netherlands, and the University of Manchester in the UK. He was then professor at the University of Calgary for 27 years, and just 3 years ago, he moved to Cape Town, South Africa. And throughout his illustrious career, he has written more than 230 publications on various topics. But today, we've all gathered to hear about his work on the Square Kilometre Array, big telescope, big science, big data. Please join me in giving a hearty Georgia Tech welcome for Russ Taylor.
Hello, can you hear me? Well, thank you, Mike. And I have to say that I am extremely honored to be here as part of the celebration of the accomplishments in life of David Finkelstein, a truly distinguished and visionary person. And I hope that what I talked about today will be something that he would have been quite excited about, and I think he would. So I'm going to talk about a very, 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 very large telescope called the Square Kilometre Array, something that I have been involved in for quite a long time. And I'm going to begin my talk by saying why we would want to build such a thing. Then I'm going to tell you what it is. And then I'm going to talk about some of the challenges that just building it presents to us and in using it as an instrument to answer our questions. So let me begin with this picture. So this is probably, you'll recognize this is a galaxy. It's a collection of 10 or 100 billion stars. And we live in such a beast in a rather nondescript part of the galaxy, about 2/3 of the way out towards the end, in orbit around a rather typical star. And that's very good for us because we're in a part of the galaxy that's nice and quiet, where presumably life could have evolved quite easily. But you see this galaxy by virtue of the starlight in it. In this picture, you're seeing the stars glowing in this galaxy. And if you do something like what the Hubble telescope did and take an image as far back into the universe as one can with the telescope, what you see is many, many more of these kinds of things. Right? You see galaxies as far as you can see. So this is the famous Hubble Deep Field. The Hubble telescope basically did a very long exposure, hundreds of hours, thousands of hours in the latest versions of this, to see what it would see, and what it sees is galaxies. And you see in this image, these galaxies are speckled in the blackness of space. What we have actually come to understand in the last 2 decades of astrophysical research is that the real questions about the universe that we have today don't really reside in these bright bits, but in the dark bits in between. These bright bits actually are a very, very small fraction of the content of the universe. The universe is made up of things we don't understand, and these bright things are little blips in that sea of stuff we don't understand. And that lack of understanding is characterized by this pie chart, where the blue things here are all the galaxies and all the things we understand to be built of the same kind of things the galaxies are built of, which is normal matter. We know that in this cold, dark space between the galaxies, there's something called cold, dark matter. We know it's there because of its gravitational influence on the galaxies. We measure the motions of the galaxies, and we know that there's got to be much more mass there than we can see, and it sits in this dark region in between. But more than that, we know that this black region is expanding very, very rapidly and is being driven by some mysterious form of energy, which we call dark energy. It's called dark because we don't see it, right? It's in the dark parts, right? So understanding these forces and these energies and this matter and the fundamental content and makeup of the universe by looking at the luminous stuff is sort of the challenge that we have in modern astronomy. Right? And the Hubble Space Telescope is going to be replaced in the near future by a next generation instrument called the James Webb Space Telescope, much bigger. It's also going to be much further from the Earth. It's going to be in the way out here in what's called the Lagrange point of the Earth-Sun system. And it sits out here on the other side of the Earth, always in the shadow of the Earth from the Sun, peering off into empty space. It will also do the same kind of experiment the Hubble Space Telescope did, of doing a very deep field. And what will it see? Well, it'll probably see more galaxies. And it'll see more galaxies because that's all it can see. Because the Hubble Space Telescope observes the universe in optical light, and the optical light in the universe comes from the stars. So it'll see galaxies perhaps further away at an earlier stage in their formation in terms of the cosmic history of the universe, but it won't be able to see what's in between, what's in the dark stuff, right? And the dark stuff, in fact, is rendered visible by radio waves, and that's why we need a very large radio telescope. Let me tell you a bit about that. So this diagram here, it plots, this bar shows the transparency of the Earth's atmosphere to wavelengths of electromagnetic radiation. Right? And there's 2 windows where energy from the universe can get down to the surface of the Earth. One is this one over here, which is the optical window, the kind of radiation we see with our eyes, and where most traditional optical mirror telescopes operate. But over here, this part is called the radio window. This is wavelengths of radiation from of order 10 meters to about 1 centimeter. And that radiation also gets down to the Earth, and we can measure that using radio devices like radio telescopes. And over the last several decades, nations around the world have built radio telescopes to detect the universe at these wavelengths. Right? These are examples of radio telescope arrays that have been built in India, here in the US. This is a very large array in New Mexico. This is an Australia telescope. This is one in Canada. This is the one in the Netherlands. There's been a vast investment in observing at radio wavelengths by the world. And what we've discovered is, in fact, it does reveal the space between the stars, what's in the space between the stars. So this is an example of this. This is a star field imaged with just a small camera by an amateur astronomer in Calgary in Canada named Alan Dyer. And what you're seeing here is a field of stars which might be characteristic of about something like that in a galaxy. Fairly large volume, and you see it's full with stars. If we take that same piece of sky and we observe it with a radio telescope, then it looks like this. Right? It's extremely different in character. Right? You no longer see a universe filled with starlight, but you see a universe filled with matter. And that matter, in fact, is called interstellar matter, and it's the matter that produces all the stars. That's where all the stars come from. This material is the seeds of new stars. And the way I like to think about it is optical light and the stars tell you the end product of the evolution of matter, but the radio telescopes show you the story of how that came into being. So it's the becoming of the end product of the universe. Right? And the same thing if you go outside of our galaxy and look at other galaxies. This is an optical image of a bunch of galaxies. This is a radio image of the same piece of sky, and what you see is that these galaxies are embedded in cold matter that you cannot see at optical wavelengths. It takes a radio telescope to see those. So if we want to understand what's happening in the space between the galaxies and between the stars, radio telescopes offer that opportunity. So radio astronomy itself is a fairly new discipline. We've been doing optical astronomy for thousands of years, first with our eyes, then with mirrors and sophisticated telescopes. But radio astronomy required the development of radio technology tool to detect radio waves, measure their intensity, measure their properties. And that began as a science only about 50, 60 years ago. And it was driven, a lot of the technology was driven by developments during the Second World War and the development of radar to detect enemy spacecraft and submarines and such. Right? So the first scientific use of a radio telescope was actually just before the war by Reber. Built a small telescope and detected radiation from outside the universe, outside the Earth. And following that, during the 50s and 60s and 70s and 80s, bigger and bigger and bigger telescopes were constructed to make them more and more sensitive. So what we're seeing on this plot, here it's time on a linear axis. Here is sensitivity increasing downward, right? So basically what we're showing is the faintest signal you could detect with a telescope as a function of time. Right? And this is the logarithmic axis. And when something is a straight line in a log linear plot, there's a Moore's law type. It's an exponential growth, right? It's like Moore's law, the rule that the amount of transistors you can get onto a square area of microchip grows exponentially with time, doubles every couple of years. What we're seeing here is an exponential growth in the sensitivity of telescopes. That exponential growth it happened for 4 decades and stopped in 1980, which is when I got my PhD, 1982. And after that, telescopes didn't really improve in sensitivity. They sort of leveled off. Right? And what we ran across there is a technological wall. We just could not build more sensitive telescopes with the technology of the time. There's a way that you get more sensitivity with a telescope is you make a bigger area, or you observe radiation over a much larger range of wavelengths, which we call bandwidth. Right? And we ran into technology walls there. We just could not do it. Right? And so during this period of time, more telescopes were built, but they did not improve sensitivity. These solid lines here are upgrades to existing telescopes. So here's the Very Large Array, the big one in the US. It just underwent a major upgrade to improve its sensitivity, and it managed a sensitivity increase of a factor of 2 or 3. What we want to do with the SKA is go back down another factor of 100, right, to observe radio waves from the beginning of time, as I'll talk about later. And that requires us then to solve a lot of technological problems. And we first came up with the idea of the SKA back here in 1990, and we've spent the last 15 years trying to solve the problem of how to make something so sensitive and I'll return to that issue later. Okay. So it's interesting to point out that during that period of exponential growth was a rapid period of discovery about the universe. Right? Things that we discovered, pulsars were discovered, the microwave background radiation, the relic radiation from the Big Bang, the creation of the universe. Dark matter was discovered, quasars, things moving apparently faster than the speed of light, not really, but looking like it. The effect of gravitational radiation, the slowing of the changing in the orbit of systems because of gravitational waves, aperture synthesis itself, 4 Nobel Prizes during that period. So I'm not bragging about radio astronomy here. What the point I'm trying to make is that when you have rapid technological advance, new ways of observing the universe, you discover amazing new things. And we want to get back on that curve of exponential growth and understanding of the universe. So we need a bigger telescope. So to build a telescope that big requires the resources of more than just one country. And so the first thing we did was form an international collaboration to help us solve those design problems. And right now, the Square Kilometre Array project is a partnership of 10 countries. The ones in colors here, you notice that the USA is missing. The USA, in fact, was an early partner in the project and helped solve some of the design issues. But in 2010, in the last review of the decadal plan for the US, the SKA was not part of the 10-year plan, and so currently it's not part of the partnership. But we certainly hope you'll come back in 2020 when you have your next decadal review of where you want to go. Hashed countries are hosting some of the telescope. Okay, so this is what the SKA is going to look like. So it's actually made up of 2 types of technology. This is an array of antennas. Each of these antennas is 15 meters in diameter, about the length of this row of tables. And there are about 3,000 of them. And what you're seeing here is the central part of the array. We're flying over it. And you see several hundred antennas within an area of a few kilometers there. All those telescopes operate together. They all point at the same piece of sky and collect data. And the data from each telescope then gets sent off to a place where it's processed and turned into scientific information. Now, in fact, to observe the universe at the full range of radiation wavelengths we want, we also have another technology, which is this one, which is what we're calling a dipole array. It's an aperture array of resonating elements. And these telescopes operate at much longer wavelengths than the dishes. The dishes are what we call mid-frequency, operating from about 1 meter to 1 centimeter. These operate from about 10 meters to 1 meter. And we actually have a third technology we're exploring, which is extremely powerful, but also very difficult. And this technology will not be used for the initial phases of the SKA. But these telescopes require a lot of digital processing, and I won't talk too much about those. Right. So what we have is a central core. It's about 5 kilometers across. And then we have antennas that go out to much larger distances. And we're going to fly along one of these arms. And the distance that we're at will show up here. And eventually we get out to dimensions of 1,000 or more kilometers. And right, big arms stretching out to 1,000, 2,000, 3,000 kilometers. The diagram turns blue here because this movie was made before the site was selected for the SKA, and we wanted it to be site neutral. Right? But that's the SKA. It's going to be 2 antennas, a low-frequency antenna made up of those dipole arrays, and a mid-frequency antenna made up of a large number of those dish antennas. And in each case, there's thousands of elements. Right? So where to build this thing? So that's what we want to build. One of the key drivers of the decision of where to build it is the presence of what we call radio frequency interference. radio waves created by human technology that pollute the sky. And this is an image taken from a French satellite at 131 megahertz looking down, and it was actually designed to look for radio frequency emission from lightning. But over the course of the many years of its mission, it produced this average map of the radio power from the Earth. And what you see here is that there's radio waves produced by human activities occupying most of the globe. And there are very few places left where you can build a telescope that's not going to be affected by such signals. And one of them is the western outback of Australia, and the other is the southern part of Africa. There's also Antarctica, of course, but it's not a very practical place to build a telescope. And for other reasons, you want to be as close to the equator as you can so that you observe as much of the sky as you can. So that's, in fact, where the telescope's being built, and it's going to be built in both places. And what's happening is that in Australia, we're going to build the low frequency, the dipole array. So there will be about 1 million of those dipole antennas distributed over a large area of Western Australia. And it looks like this, which is why there's no radio frequency interference there, because there's nothing there. There's a lot of sheep. And in South Africa, we are building the mid-frequency dish array with the core of it, the core several tens of kilometers in a high plateau in South Africa, which is why I'm there. And it looks like this, rather similar to the Australian site. Not very much going on. That's, in fact, part of the SKA installation. But we will remember that the baseline for the mid-frequency arrays goes up to thousands of kilometers, so we will have stations through many, many southern African countries out into Mauritius, Madagascar and Mauritius in the Indian Ocean, and all the way up to Kenya and Ghana, so that the hosting of the SKA in Africa is not just a South African installation, but it's going to have 8 African partner countries. Okay, so what is the timeline? We hope to build the entire thing within the next 10 years. It's going to be built in phases. There's a phase 0, a phase 1, and a full up phase. And the phase 0 phase is 1%, and that 1% construction began in 2015 and will be completed early next year. 1 year from now, we will have the 1% completed, and that's called MeerKAT in South Africa. And we have, in fact, an operational 1% scale demonstrator in Western Australia called the Murchison Long Wavelength Array, which is a prototype of the full low-frequency SKA. The 1% scale telescope will operate for 3 or 4 years and then be integrated into the 10% scale, which is called SKA Phase 1. Which will begin construction around 2019 and be completed around 2022. It will then operate for 3 or 4 years, and then the full SKA, the 90% scale, the 100% scale, will begin construction around 2023, and hopefully complete around 2027 or 26 or 27. So it's a factor of 10 scale out in each step, which offers a lot of advantages. One thing, we can do that because it's an array. Right? You don't have to build all 3,000 antennas at once. You can build 100, then you can build 500, and then you build 3,000. It also allows you to learn along the way. So there were lots of technological innovations that had to be solved to build the SKA, but technology innovation, of course, is not something that stops. At some point, you have to stop and freeze the design and build something, but technology innovation continues even after you've frozen the design. So this phased rollout allows you to take advantage of new technology development, because the design of the full SKA won't be completed until SKA Phase 1 is operational. We'll learn all the lessons. We'll be able to take advantage of new technology development to make the SKA, the full SKA, more powerful than it would be if we had to build it all today. Okay. So that's the SKA and the timeline. So let me talk a little bit about why, over and above the fact that we need a radio telescope to peer into the dark universe, what actually are the science questions that we plan to address with the Square Kilometre Array. So this is a 2-volume 2,000-page document, which is the SKA Science document, created following a conference that we had in Italy 2 years ago, containing 1,300 different science goals that scientists around the world want to do with the SKA. It's a massive volume, contains a lot of detail. But what I've done is I've distilled, I think, the science drivers for the SKA into a few sort of large picture issues, which I'll, okay. So the first one I call, the history of time, complete history of time. Right? Essentially, we want to understand how the universe we live in came to be. Right? And we have our bare bones of that story. We believe that it was all created in something called a Big Bang, and that after the Big Bang, somehow structure evolved in the universe. The Big Bang, we know, was almost a completely uniform glow. Right? There was hardly any structure in it. It was less structure in that than there is in a billiard ball. Right? It was extremely smooth. Somehow that very, very smooth, chaotic event created complex structures evolving into life eventually. We know some of the steps along the way. We know that form galaxies. We know galaxies form stars. We know some planets formed around stars, and we know that on some planets at least one life evolved. But that's the very, very sort of outline look at the universe. Right? What we want to understand, for one thing, well, is all this sort of necessary? What were the physical conditions or the laws that gave rise to this embedded in the fabric of the universe at creation? Right? Is it destiny or is it chance? So to understand that, we need to know all the steps, and we need to know all the logical chain of events. Right? If A, then B, if C, then D, if D, then F, all the way from A to Z, or Z, I'm sorry, all the way to A to Z. Is that a logical chain? Is that a necessary chain? Right? Does this arise because that happened, or is something else happening? Right? So complete history of time is one of our goals, and to do that, we're going to make this complete history of the universe, right? The universe in a cube. So we're going to, this is a schematic of the major phases that happen in the universe. This is the Big Bang. This is the present day. This is the Hubble Deep Field, showing the fact that the universe today is filled with these galaxies. Between there and there, there's something that we call the Dark Ages, when there were no galaxies, there were no stars, so there's nothing to see with an optical telescope. But these dark ages between then and here is actually filled with stuff, and that stuff can be rendered visible with a radio telescope. Right? So we're going to build this three-dimensional picture of the universe all the way from here to back there and understand how this came about from that. And this is a picture of simulation of what we might see when we look at that part of the universe. We'll talk about how big that cube is in a minute. Okay. The other big question is, what in fact is the fabric of reality? What is reality actually made of? Right. And this is something that David Finkelstein would have been really keen to do with the SKA. Right? Because it's the question of what is the fabric of space-time. And of course, the big challenge of our understanding of space-time is how to reconcile the quantum view of the universe, that everything is quantized on the small scale. It comes in little bits. It doesn't come in a continuous wavy thing. With Einstein's theory of general relativity, which says that space-time is curved by gravity, but it's a continuous manifold, topologically. And the way to understand, or the way to examine the universe in a way that will answer those questions, is to look at the universe in places where the curvature of space is so high that you need to understand the quantized nature of it to explain the phenomena. Because the curvature happens on the quantum level. And that, of course, happens around black holes. Right? And so we have these wonderful things called pulsars that exist out in the universe that were one of the Nobel Prizes in radio astronomy. And the SKA will have sufficient sensitivity to detect basically every pulsar in our galaxy. And it will have sufficient sensitivity to time them to exquisite resolution. Right? So basically what we will have is a very stable clock orbiting very close in to a black hole, and we'll be able to measure the properties of the curvature of space-time under what's called strong gravity situation, where the curvature is extremely high. And that will be rendered possible by the SKA. The other aspect of gravitational fabric of space-time is gravity waves themselves. Now, you will have all heard the wonderful news that gravity waves have been detected by human beings with the LIGO experiment, and the people here at Georgia Tech have been part of that endeavor. And the way that that measurement is made is by taking a distance between two things on the Earth and measuring it very accurately and waiting for it to ring and measuring that. Now, that was done very successfully, and it's a tremendous technological feat. But the other way to measure waves in space-time is not through space, but through time. And as I said, we have these pulsars out in the universe. If one of these curvature waves in space-time floats by and goes by the Earth, what it affects is that the travel time of a radiation wave from the pulsar to the Earth is bent a little bit, and the proper time of propagation to the Earth changes because of this wave passing. If you have an array of these things on the sky, you can look for coherence in arrival times of signals from an array of pulsars and see these waves propagating by space around the Earth. And these are very, very long wavelength things. The gravity waves detected by LIGO were very high frequency, short wavelength. The whole thing lasted about a fraction of a second. It was like that, and it was over. Right? These things take a long time to propagate. Right? So what you're measuring with this technique are very, very long wavelength gravitational waves. And this is a plot of frequency versus amplitude here. This is the LIGO experiment with the ground base. These are very, very fast. These are sort of hundreds of hertz signals. The ones that we will detect with pulsar timing arrays are much, much slower. And that means they measure events which take much, much longer in time to happen. Right? So this event is the merger of two black holes very quickly of stellar size. With this, we'll measure the merger of black holes on galaxy scales. Right? Million solar mass black holes, which may be merging in the evolution of the universe and the formation of galaxies, may be forming during the dark ages before galaxies formed and interacting. There's this background of this gravity wave phenomenon, which must be happening way out there in the early universe as part of the formation of structure at the early times. And that's what we're going after. So that tells us something about the fabric of space-time. The other big question is, are we alone in the universe? Is there other life out there? Most scientists would say that it's quite likely. If you look at the Earth and the examples of life we have on Earth, basically anywhere you look, there's life. Right? Life seems to take hold and grow without much coaxing. Right? Is that same thing true off the Earth, out in the universe? Right? Well, we don't know, but I think the SKA is going to give us the answer. And it'll do this in two ways. One is by looking for the evidence of life, or the building blocks of life, out in the universe. And you know that in the last 20 years, we've discovered planets around a lot of stars. When I was a grad student, and we didn't know any of the planets outside the Earth. And it was a real speculation, is the Earth a unique phenomenon? Is the solar system a unique phenomenon? Some crazy accident that happened that created this system of bodies orbiting around our sun? Well, it's not. There are planets almost everywhere. There are about 1,000 stars known now to have planets. Even our nearest neighbor, Alpha Centauri, which is only 4 light years away, has a planet, and it appears to be in the habitable zone, so there could be life there. Right? But how do we know? Well, one thing we can do is to look at those kind of places for evidence of the kind of things that we are built of, the sort of biological molecules, the long chains of carbon and hydrogen and oxygen and nitrogen, these sort of biological molecules, long chain molecules, they radiate in the radio. And And the way to think about it is if you have a string and you pull it really taut, really tight, and you pluck it, you get high frequency modes of vibration, right? It vibrates at a very high frequency. If you make it looser, the tones go lower. Right? Think about the same thing about electromagnetic radiation. Optical radiation is a very high frequency. You need a very, very tight bond to make radiation from a molecule in optical. And that usually means small diatomic things like carbon monoxide or things that are very close together and vibrate very rapidly. These things are like woofly ropes. Right? They're very loosely bound together, they're very long, they oscillate at very, very low frequency modes, and that produces radio waves. The radio waves also are not stopped by things. Right? Your cell phone will work in here because radio waves go through the walls. Optical photons will not go through the walls. Right? So these things are enshrouded in a dust cloud from the early formation of planetary disks. Optical light does not escape. Right? So, but we can probe those regions of where planets are forming around stars with radio waves because we can actually get all the radio waves will go all the way in and all the way out, and also because if there's any biological molecules there, they will radiate at these radio wavelength frequencies. So by optical radio spectroscopy, we can detect the presence of biological molecules in these places. And you can bet your boots that if there's biological molecules there, life is going to arise. The other way to detect life is through the detection of signals produced by intelligent beings. This is called the search for extraterrestrial intelligence, something that scientists in the US have been involved in for quite a long time. The SETI Institute out at Berkeley. If you think about the signals coming from the Earth, show this plot again of the radio frequency interference or the radio emissions coming from the Earth as a function of position. Imagine this on a ball that's rotating. If you look at it as the ball rotates, the signal is modulated. As the east coast of North America rises, go wow. As it sets, you lose, right? Same thing with Europe. And you get something like this. This is basically what this would look like if you measured it over a period of a day. You have a strongly varying radio signal. And some of those signals have lots of information in them. Some of them are radars that are triggered and pulsed. Some of them are actually radio signals that are carrying television shows or radio shows. So they're information-rich radio signals. And if you ask yourself, what would it take to detect something like that? Well, it's a square kilometre array. Okay. So as I said, the SETI has been going for, well, I think in the 1970s or 60s were the first experiments. Bad transition, sorry. This is that galaxy I showed in my first slide, and this is the distance from the Earth, which is, say, here, out to which you could detect this kind of signal. Our early attempts are the little red dot in the middle. Only the very nearest stars could we have detected something like this. The green circle is a limit for something called the Allen Telescope Array that was built by Berkeley in California. It never actually got completed, but this was its planned search radius. The Square Kilometre Array in 1 year could search a large fraction of the galaxy for these signals and detect them if they were there. Right? So even if there's only a few of these kind of civilizations in the galaxy, we'll detect one. And if we don't detect one, it's also a definitive answer. Right? We know they must be very rare, right? Because we can see such a large volume of the galaxy. So the SKA, within about 3 or 4 years of turning on as a full 100% instrument in the late 2020s, will I think definitively answer the question, is there other intelligent life in our galaxy? And my bet is that it will find one. And what's really fun is that it'll likely be detected by some person in their basement running a screensaver to search the data. In which case it'll be on social media very quickly. Okay, so those are the three big ones. What is the fabric of reality? What is the complete history of time? And are we alone in the universe? And I think they're really questions that I really want to know the answers to, and I think most of us do. So let me talk a little bit about the technology path to the SKA. We had to solve 5 big challenges. One was large collecting area. We needed a factor of 100 increase in the collecting area. And if we did that with the technology available at the time in the early 1990s, it would have cost us about $100 billion. We had to get the cost of collecting area for a radio telescope down by a factor of 100 to build 100 more times more area. To address our science goals, we want to be able to observe a large parts of the universe all at once. We can't learn what we want to learn by looking at very, very narrow bits of the universe. We need to map the whole universe. That means we need to have a combination of a large field of view, a very wide field imaging device, and large bandwidth, because bandwidth turns into depth out in the universe. So large field of view, large bandwidth, that required development of digital technologies and radio receiver technologies, which allowed us to image very, very large areas and to detect radiation over very large ranges of wavelengths. The scale of this device, it's 100 times bigger than any radio telescope array that exists, means we had to figure out how to do it with low power consumption. So we had to get all of those increases in capacity in digital electronics and antenna construction and data transmission at no increase in power. In fact, a decrease in power is better because it's going to take 100 megawatts to run this thing. And the combination of large number of antennas, large field of view, large bandwidth derives a massive data set. So those are our real big problems. The first 4 are construction design problems. The last one is an operations problem. So I mentioned this as a global collaboration. The way that we are working on the design, we spent 15 years solving the technology problems, coming up with conceptual ways to actually solve these challenges. And during that phase, the US was one of our partners. We had 120 institutes around the world working in a sort of a cooperate to compete mode, right? Where we all wanted to achieve the same goal, but we wanted our solution to be the one that solved the problem. And so every year we would meet and present our ideas and hope it was better than anybody else's ideas. And it was a really interesting time to be involved in the project. We made very rapid advance in technologies. And around 2008, we narrowed it down to a few best winning ideas for how to build a telescope. And since that time, we're in what's called the final design phase. We're taking those best ideas and turning them into detailed designs that we could actually give a contract to companies, say, here, build this. Right? And that detailed design is being done by the international collaboration, and we have 10 what are called work packages working on the detailed design of the various elements of the device that we have to solve. And that all will be finished next year. Oh, wrong one. Okay, so we are building the first 1% of the mid-frequency array in South Africa. This is called MeerKAT. And this is some of the antennas on the site. And it's, this plot here shows the population density of South Africa. And where it's blue and red, where it's red, it's the major cities. There's Cape Town, there's Johannesburg, there's Durban, Port Elizabeth. And where it's white, there's very few people. Right? And these are the dots which show the location of the core of the SKA, and the purple dots going off are the remote stations of the SKA. You'll notice that these antennas look different from your typical radio telescope. When I showed you the arrays that we built over the last several decades, they were called center-fed. They're symmetric. There's a parabolic circular dish and feeds going to the center point. Those are called center-fed parabolic antennas, and that's the way we built telescopes since we started building telescopes for the radio. This is our new design. It's called an offset parabolic. These are still parabolic shapes, but half is missing. And the feed, instead of being at the middle, is off on the side. Here, see one here. And in fact, we have what's called a subreflector here. So the radiation comes in from space, hits what's called the primary reflector, gets reflected then to the subreflector, which focuses it into a receiving system here, which detects the radiation and turns it into digital signals. So this has a radio frequency device that, like an antenna, that samples the radiation pattern or the energy of the radiation over broad wavelengths. And attached to that, we have a device that turns that into a digital signal, which then gets transferred by optical fiber to the center. Right? And the advantage of this offset feed system is A, it's much cheaper to build, and B, it's much less sensitive to radiation coming from places you don't want to look. Right? And what's shown here is what's called the beam pattern, or the reception pattern of the array. And you see this conventional antenna. This spike in the middle is the radiation coming from the direction that you want to detect radiation. All this garbage here is stuff coming in from other directions, which you don't want. And it's scattered into the receiver by the feed legs, right? Radiation coming in from the side, hits this, bounces off that, and goes in there. You don't want that, right? This kind of feed, the radiation comes in here. There's no way for the radiation to get here from any other direction except the forward direction. So that and produces a pattern that looks like this, right? Where almost virtually all the energy comes from the direction you're looking. That makes the antenna much more efficient, much more sensitive, and it also reduces your sensitivity to radio frequency interference, things coming in from other directions. Right? Talking about radio frequency interference, this is a spectrum showing radiation power as a function of frequency here. And this is the range of frequencies that we need to sample to make our map of the universe. And this is the radiation power produced by civilization in inner city. This particular one is Sydney, but I'm sure Atlanta would look pretty much the same. There is no place here except maybe there where you can observe without being corrupted by signals from cell phones and radars and televisions and radios. Right? Even a small town, this is Narrabri, which is a small town, population 4,000 in Western Australia. It's better, but there's very few places where you have a quiet sky. Right? This is the spectrum at the site for the Western Australian low-frequency array. Right? It's extremely clean, but there still are areas where there is radiation. In fact, these are primarily satellites, low Earth orbit satellites that are beaming down, mostly telecommunications satellites. And there's no way on the Earth you can go to get away from that. It's everywhere. The people that make these downward pointing radiating satellites don't turn them off when they go over radio telescopes. They just keep on transmitting. So we have to, even though we can go to a very quiet place, so we can't get rid of it entirely. And so we have to mitigate that radio frequency interference, and that requires very sophisticated and powerful digital electronics. Oh, geez, I'm sorry. Okay. So we have to develop new digital technologies to operate over wide bandwidth, which means we have to channelize that wide bandwidth in millions of channels so that we can detect and remove the interference, and also to make our map of the universe. So we have to have real-time processing intelligent systems which look at that data and say, oh, this is a bit of interference. We'll flag that and remove it. This is not. And requires, there's no human being that can do that. Right? We can't send the data off to a grad student and say, look at this, remove the RFI, then send it back. Has to be done in real time with exabytes of data flying down a pipe. So it requires machine learning and artificial intelligence and automated processing, which we're in the process of doing. Currently, the largest device of this type is the one at the Very Large Array, built in Canada. The correlator built in Canada, I should say. And, but the one for the SKA will be 1,000 times bigger than that. Okay, so that, I'll end off now talking about the data. So we built a monster, essentially. We built a data monster. We have really high ambitions to observe the universe in these wonderful ways, to answer our fundamental questions about why we're here and what's the universe like, what's it made of, are we alone? But to actually answer those questions, we have to deal with this data monster. And this is a data view of the Square Kilometre Array. So what we have here, these are the telescopes. These blue things here are either the dipole array in Australia or the dish array in southern Africa. And there's a data stream coming off of each one. Not extremely terrible, maybe a terabyte a second. Right? And comes off an optical fiber and gets aggregated. Right? The closer you get to what we call the signal processing facility, the larger that data stream becomes, because we get more and more antennas as you get closer. And that data system then hits our signal processing facility. Now, the data that is processed here is, well, what this data processing facility has to do, it has to take each of those 3,000 data streams and multiply pairwise every possible pairwise combination of those 3,000. And take it over a certain bandwidth, shift it, multiply, and spit out the correlation coefficient, and it has to do that every nanosecond. So this is not a general purpose data problem. It's a specific thing. We know what we want to do with the data. It's a specific thing. But it's, when the SKA is fully operational, it's 10 exabytes a second, which is larger than any computational problem that's actually done anywhere in the world now. Places like IBM have plans to get to the exascale computing level, but they're not there yet. So this is a problem we haven't solved yet, and there's a nice quote from Bruce Elmogreen from IBM Research in Watson Labs in New York, that the data rate in the SKA will be comparable to that circulated around the globe by the rest of humanity when it turns on. So basically, all the data we produce on the internet every day, every second, the SKA will produce data at that rate. So that's a big challenge. So we need to build this, and this is an engineering challenge. Once that data is processed, it gets spit out on this side. It gets spit out at a slightly smaller rate, about 100 times smaller. So it's not exascale anymore. It's sort of 100 petascale challenge, which goes to a computing facility, which has to do some real-time processing on the data, which reduces it then by maybe a factor of 10. And the data reduction here is a compromise. You have to throw out some data here with current technology, right? Because we can't actually handle that flow through at the current, with current technology. But as things get better, we hope to be able to do that. And anyway, data coming out of that then goes to regional centers around the world, which host the data, which is the data, in fact, that is used for science. So this facility converts the data from the correlator into data that can be used by scientists. And in fact, this is where the complex things to do to the data reside, things you don't already know what to do. This is a single purpose engineering problem. This is a general purpose science problem. And that's where the rubber hits the road. And this shows you a plot of how that's sort of evolving with time. This is similar to the plot I showed at the beginning of radio telescope sensitivity versus time. Only this is now time on this axis and data rate or data volume on this axis for large science projects with radio telescopes. And again, if you have a straight line on this plot, it's an exponential growth, and you see that there's been an exponential growth from about 2000 to now, largely driven by advances in the first world. This is the Arecibo telescope. This is a very large array. This is a very American-centric view here. But basically, data has been growing at a reasonable rate over the last little while. But what's going to happen when the SK turns on is you get this curve. And that curve happens in Africa. And I have to say that Africa is less well prepared for this than North America, than the US is. Right? And so when I show this plot in Africa, I basically tell them, if we don't solve this problem, these are the people who are going to do the science, not Africans. Right? So what we're working on in Africa is, in fact, to put in place the systems which allow us to deal with that data and to allow African scientists to be full partners in the science with the Square Kilometre Array. Even here in the US, you can't solve this problem yet. So it's a big one. So this is sort of what the data looks like. The data coming out of that science that science device spits out images. And this is what an image might look like. I blurred it out here. Remember, at the beginning of my talk, I showed the Hubble Deep Field, which is full of galaxies. In this image, there are several thousand galaxies. That little thing there is the scale of that Hubble Deep Field on a typical image that will come out of the SKA in an observation of a day or two. So if you imagine this, this is the size of the moon, so it's a very large piece of sky. It's that wide field imaging capability. So several thousand objects here. In this object, there's hundreds of millions, or there's hundreds of millions of objects in this image. And recall that this is only one of maybe 1 million channels of radiation. So you have here, say, a terapixel image, and you have 1 million of them, so your sort of petascale images coming out of the device on the time scale of a day or so. So over a year, you'll have exascale data sets, and you have to mine them for what's in there. The questions are we alone? What's the fabric of the universe? What's the complete history of time? It's all in there. Right? The question is, how do we get it out? Right? And that's the challenge. Right? And not only that, right? We have a new way that we're going to be doing science with the Square Kilometre Array. Right? So the sociology of radio astronomy is fundamentally changing. This is the way things used to work when I was a grad student. This is the Very Large Array here in the US. I would write a proposal to observe a certain thing, a certain object, because I had an idea and I wanted to answer follow through on my idea. Write a proposal. I might get 5-10 hours of time on the VLA. I would go there, I would observe, put a floppy disk under my arm, come back to my university, read it into my little desktop computer, process it, make it an image, analyze it, write a paper, and cycle. Right? And it used to be the old generation radio astronomers, that was their life. After 40 years, they retire, having published a few hundred papers. It doesn't work that way anymore. Now radio astronomy is big science. We don't build national facilities, we're building a unique global facility that are meant to answer fundamental questions about the universe, and every astronomer in the world who's part of the project wants to be part of those fundamental questions. So we have big questions, big project, big collaborations. So this facility is now feeding the world, and it's feeding global collaborations around the world who all want to be part of answering those questions. They all want to be part of it. But none of them can have the data because the data is too big. And the MeerKAT telescope, the 1% SKA, is pathfinding that mode of operating. It's going to do what are called large survey projects. It has 10 projects, which over the 5-year operation lifetime of MeerKAT before it gets integrated into SKA phase 1, will take most of the time of the telescope. So each one of these projects gets thousands of hours of time on the telescope, producing really, really big data sets. And example, Duma is one of these ones that's going to make this cube of the universe, not all the way out because it's only 1% of the SKA, but as far as we can go. This is imaging the early universe, the bright things in the early universe, et cetera, et cetera. This is looking for pulsars. This is the gravitational wave experiment. These projects have hundreds of researchers attached to them. They get lots and lots of time on the telescope, producing lots and lots of data. So the new mode of operation is not only creating these large data sets, but how do you allow researchers all over the world, none of whom can have the data, to do their research with the data? So we have to think of new ways to do this. And this is just an example of for the MeerKAT, the distribution of countries and researchers involved in those projects. So we need somebody from the US, somebody from Canada, somebody from Mauritius and South Africa, all working on the same project to somehow work together on data that none of them can have. So not only that, you don't have just the problem of how to work on the data from the SKA, but many of the science goals require us to compare that to data from other telescopes. Here in the US, you have the Large Synoptic Survey Telescope, the LSST, who's going to be making images of the sky every week and dumping those data for PIs to observe. We want to jointly analyze SKA data with LSST data and with data from space telescopes and data from other telescopes. So we need to somehow fuse all the data from all over the world with the SKA data to do our science. Not only that, but we also, in order to interpret the data, we need to compare it to simulations. So we get this big cube of the universe. One of the best ways to understand what's in that cube is to compare it to simulations. Simulations being model universes that we create based on assumptions that we make about the nature of the universe. Right? So you postulate some cosmology, some laws that existed at the beginning of the process. You turn on a big supercomputer and you create a model universe and say, well, the SK should see this if the universe is the way that I think it is. Right? How do you compare those two things? You have a big simulation, that's a big data set, and you have a big SK data set. So you have the problem of fusing observational data from the SKA with simulations coming out of supercomputers and smart people that simulate the universe. And these are some examples of simulations of bits of the universe on different scales. And we need to compare what we observe to these things. Right? How do you do that? So we have this issue of generating knowledge from big data observations, big data theory simulations, and big data multi-wavelength data sets. So these are the four core challenges we face in turning the data from the SKA into the answers to those questions. Just the sheer fact that we have such large data sets, exponential increase in rates and volumes. The fact that we have to process this thing in very complicated ways, and in fact, ways that we don't really understand yet fully. We have initial ideas, but it's going to be the case almost certainly that once you process it once, you say, oh, geez, I should have done it differently. Oh, look at this. What do I do to make this aspect of the data more apparent? So you need to process things in different ways. You need to fuse it with big data from simulations and observations. And you have this problem of collaboration. Right? Researchers from all over the world all wanting to work on that data, but none of them being able to do so. So we need a new way of dealing with data. Right? And there was a really cool book written by Al Gore called The Future, 6 Drivers of Global Change in 2013, where he identified 6 things which are going to change humanity in this century. And of course, the digital data transformation is one of the big ones. Right? And we need to develop a new generation of technologies to allow things like the Square Kilometre Array to answer its questions. But fortunately, we live in a time where there's a tremendous and rapid transformation in digital technologies. Right? We're living this data revolution. Right? 10 years from now, we'll be in a very, very fundamentally different world in terms of what happens with data, how we can work with data. And we have this revolution where collaboration is being enabled by internet technologies and social networking and various ways to allow communities of researchers, communities of people to gather around an idea and to exchange ideas and work with each other. So the trick is to capture that revolution and make it work for the SKA and for astronomy in general. And what we're doing in Africa is we're working on a project called the African Data Intensive Research Cloud. Excuse me. Using cloud technologies to enable research in these data-intensive areas. And the institute that I work with, we're building a prototype. It's a collaboration between our 4 universities. And this basically takes distributed resources. It takes high-performance computing, large data sets, bring them together in a distributed way. So you may have some data here and some computing there, other data here, other computing there. But the user enters into this cloud technology through a scientific gateway, and where the data is, where the computing is, where the storage is, they don't care. They just access a big supercomputer through their iPad or their desktop, right? And it's like they have the data on their computer. So these are the technologies that we need to bring to bear to solve these problems. And that's just the architectural side of it. On top of that, of course, we have, even if you have all the computing and all the storage on your desktop, how do you tease out the answers? How do you analyze data from a billion objects and at the same time look at the optical data, the infrared data, and characterize these objects? That requires automated approaches to dealing with the data. You can't go away and look at a screen and point to things and draw graphs on pieces of papers. You need to use new technologies. And so we're looking at machine learning, artificial intelligence, ways to go into the data and to mine it, guided by human intelligence, but aided by machine intelligence. And those are the kind of research areas that we're looking at. So I'll conclude by saying that when we have this working, the idea is to establish a global network of centers where this kind of research is happening and where we will enable the blue people here, which are individual researchers, to access the data and use these tools to extract from data sets like the SKA the answers to our questions. And so like the SKA itself, we have a global telescope, but we also have a global big data solution to mining the data. And that's the end of my talk.
Thank you, Russ, for the wonderful talk. We have some time for some questions. So, yes, we'll take you first, then you.
Thanks. Could you talk about what determines the placement of the antennas and how you compensate for the variations in phase of the arrival of the signal of those different antennas?
Okay, yes. They're two separate questions. They're not linked, but are you an engineer?
I was.
Okay, you know about Fourier transforms?
Yep.
Yeah, okay. So there's a Fourier transform relationship between the placement of the array and the image. Basically, every pair of antenna gives you a coefficient in a two-dimensional Fourier transform, and you transform all the coefficients you get from the antennas to get the image. So any regularities in that distribution turns up as an artifact in the image. So the core array of several thousand or several tens of kilometers, they're randomized, so that there's no regularity when you make the transform. So there's no artifacts from the fact that you get gratings and such. When you get further out, you lose that capability because you can't populate out to 1,000 kilometers randomly. It's just not cost effective. You have to go where the data connections are. So you sacrifice that. And on the arms that go out to large distances, the placement is a geometrically increasing separation with distance. And that gives you a self-similar array pattern, so that when you scale with frequency, the Fourier transform sampling scales in a self-similar way. And so that's what that comes from. To make those correlations between the data streams from the antennas, you have to shift them so that the data stream lines up. And of course, there is a big delay between the arrival of the signal at one antenna and the other. And there are many, many things that affect that delay. And you need to get that delay down to nanosecond scales. So the instrumental part of that, the geometric part you can solve. It's a general relativistic problem. You have to worry about the curvature of the gravitational field of the Earth affecting the propagation time of the radiation. And the instrumental part, the phase path between the antenna and the correlator along that optical fiber, you can measure that by sending signals back and forth and measuring the delays. What you can't correct for is the atmospheric. The fact that the radiation is coming through the atmosphere will affect the arrival time. And for that purpose, we have a small window of delay that we shift and multiply, and we look for the peak in the correlation function.
So thank you for that. Your lecture was such a model of clarity that although I took my last physics course more than half a century ago, I understood everything that you said,
Cool. Except
except for your answer to this question. So exactly half a century ago, Shklovsky and Sagan were preparing for joint publication. Their independently arrived at calculations which when I read them made it seem extremely implausible to me to doubt the existence of intelligent life elsewhere in the universe, and you seem to agree with that position. But last year I was at an astrobiology conference where all the astronomers doubted that there's intelligent life elsewhere. So I didn't know anything about astronomy. I knew a lot about evolution, and I said, well, okay, if the conditions are right, it pretty much has to happen. And the conditions are right in a lot of places. So my question is, if aside from holding my breath for 10 years and getting the definitive answer from the SKA, with all that we know now about habitable zones and the number of galaxies and all the better information we already have, why are people still doubting that it's out there?
Good. It's a good question. You saw my quote from Jodie Foster in my talk. She also had another really good quote from that movie, Contact, was that if there's nothing out there, it's a tremendous waste of space. Personally, I think that it's very likely. I mean, you don't know until you find it, but I see no reason why to doubt that there should be life elsewhere. The history of human perception of the nature of the universe has grown in stages, and the idea that we are special has always been a bad idea to host, right? We used to think that the Earth was the center of the universe, that everything revolved around the Earth because we were special. That's no longer true, right? We used to think that our galaxy was the only thing in the universe, but now we know there's galaxies out as far as we can see. So ideas that are generated from the proposition that we are special, I think, we need to be very suspicious of. And I think that sort of underlies the doubt and the questioning about, is there other life out there? Because it removes our special nature. If there's other intelligent life out there, we're just one off, right, instead of the unique. So I think there's a philosophical and, in some sense, placing ourselves in the universe, which is at stake in this question. And some of us are comfortable with not being special, and some of us are not. Right? And so I think precisely that reason, that is the one question which I hope the SK answers, because I think it is the most fundamental question that we can ask about ourselves is, are we the only intelligent life in this universe? Yeah, I'm really looking forward to the answer.
Any other questions? Has to be. On the back.
Okay, so when you started your research or your studies, you said that you thought it was believed that Earth was the only planet. Did you predict, like, when you started, how far, like, the SKA could be a reality? And then looking even past the SKA in, I don't know, a century or tens of years, where do you think we'll go next in research and data, and what do you think?
A really good question. I guess I've always felt that there's probably life out there on other planets. I remember reading as a young boy these ideas that some freak thing happened, like another star came by our star and struck some matter off the sun, and therefore it's a unique and unlikely event that formed planets. It somewhat didn't sit well. But I think that we will detect life. We will detect intelligent life, and it will fundamentally change the way we think about ourselves, and hopefully maybe have a good influence on the planet and our conflicts that maybe will seem smaller if we know that there's more than just us here. And but I think that you saw that picture of the Earth and how civilization is basically polluting the skies with signals. And I think that probably 30 years from now, we couldn't build the SKA on the Earth, because there wouldn't be any place where we could look and not see our own signals. And where we have to go, I think, is the other side of the moon. I think the next big telescope after the SKA will be built on the far side of the moon, where we're sheltered from the Earth. And I'm sorry I'm not young enough to see that.
We have time for one more question. Yes.
I was wondering, how does the challenge for the signal and data processing for the SKA compare with what's been accomplished with the LHC at CERN? And has that served as a model at all as far as your exploration of solutions to your problems?
Yeah, we have very close conversations with the LHC. The LHC, up to this time, it's a different kind of problem. What happens at the LHC is they have an experiment and they produce vast data sets of various particles flying off, and you measure trajectories and intensities and directions. And they harness computing systems around the world. They also have a global network, but it's a grid, not a cloud. And it works for them because they have one thing they need to do with the data, and they distribute the computing to these other centers around the world, and they send back to the center the results of the computing. And the computers, say here in the US or in Canada, are actually managed by the central system back in CERN. Right? So it's a single dedicated job that they farmed out the computing on. Right? For the SKA, we have a much different situation where we have global collaborations of researchers wanting to work with the data and do different things with the data and interact with it and explore the data. And that's a different kind of problem. But the LHC is undergoing an upgrade, and they're actually looking at what we're doing and saying, well, that's where we need to go. And so we are working with them on taking our concept of a high-performance distributed cloud system that allows researchers to interact with the data individually for that purpose as well.
Okay, so those were some great questions, but if you want to ask more questions, we'll stick around for another 15 minutes. You can come down and ask questions one-on-one, but let's thank Professor Russ Taylor again.